All right, welcome back, everybody. Today we are going to be talking about right triangle word problems, application problems. Our objective is that you're going to be able to draw the appropriate word picture. I think they mean appropriate picture to represent the word problems, and then solve for the missing information using SOHCAHTOA. So today, in a nutshell, this is what we are dealing with. We are using what we call the angle of elevation and the angle of depression to sit there and create a right triangle to estimate distances. So, for example, we have this lovely gentleman who is standing up here on his third-story balcony, and he's looking out. Now, one of the most important parts about this idea is this idea of a horizontal. So, if you were to just look out at any given point, it's when you are looking out straight. And one thing to know about the horizontal is that the horizontal always runs parallel to the ground over here. And that's what allows us to build these triangles. Now, when we come over there, in this situation, there's two things. So he first gets out there, he's standing with his coffee in the morning, and he notices he can hear an airplane overhead. So he decides to tilt his head up. When he tilts his head up, that's immediately an angle of elevation, right? Elevation means up. So he adjusts his line of sight so that he can come over here and view this triangle. As soon as he does that, what happens is he has now created a right triangle with the horizontal that he was looking out previously. Now his line of sight up to the airplane and the distance from the airplane down to his horizontal. The same thing can be true as if he notices a car driving by and he decides to tilt his head down. As he tilts his head down, we start to call that angle that he adjusts his head the angle of depression, right? And again, we can see that another triangle is formed here. And we know a lot about right triangles at this point in our lives where we can use right triangle trig to solve this. So let's take a look at what this looks like in an example. It says, a building 21 meters high casts a shadow 25 meters long. So I like to always draw a picture, because without a picture, these kind of get to be a little bit hard to understand. So here's my building. It's 25 meters tall. It's actually 21 meters tall. It's currently casting a shadow. Right, so here's the shadow of the building that is 25 meters long. And what they want to say is find the angle of elevation to the sun to the nearest degree. Now, if it's casting a shadow, here's what we know. We know the sun has to be sitting somewhere up over here. So the sun comes down, we can see its rays, it gets blocked by the building, that's what creates the shadow, and it lands at a point over there, which would be the top of the shadow. Now what we're being asked to find is the angle of elevation. So what is the angle needed to look up at the sun from that point? Now in this situation, since we're looking for an angle, we're going to call it theta. So using theta as a reference point, we know that this would be our opposite side and this would be our adjacent side. So coming over here, since we know our opposite and our adjacent, we're going to use tangent. So the tangent of our angle theta would be equal to 21 over 25. Since we're looking for the angle, let's use tangent inverse. So tangent inverse of our fraction 21 over 25 would be equal to our angle theta. Now is where we want to pull up our calculator. So second tangent of 21 divided by 25 would tell us that our angle of elevation, how far would we need to look up to see the sun, will be 40.03 degrees. Right, that is what theta is in this problem. So what that corresponds to means that this is 40.03 degrees to look up. Let's take a look at another problem. In the next problem, it says a guy wire is 15 meters long. It supports a vertical television tower. The wire is fastened to the ground 9.6 meters out from the base of the tower. A guy wire runs from the top of the tower diagonally to the ground. So, in this situation, we have a tower. I don't know what a tower looks like. I'm picturing it like maybe it's like a telephone post tower. So we have our tower, a lot of different things to secure this. Sure, I don't know what a tower looks like. That's my tower. Now this tower has a guy wire attached to it, and a guy wire, it tells us, runs from the top of the tower diagonally to the ground. So our guy wire comes down like so. Now I'm actually going to change my tower. I don't like it anymore. I'm just going to make my tower just kind of go straight up and down like this. This is my tower. This is my guy wire. Now, what we know is that the guy wire is 15 meters long. So the length of the wire to the ground will be 15 meters. Now, it also tells us that the wire is fastened 9.6 meters out from the base of the tower. So the base of the tower to where the guy wire is fastened is 9.6 meters. Now, we created a right triangle here with the base of that tower. And what we're being asked to find is calculate the angle that is formed by the guy wire and the ground. So the ground obviously is the red on the bottom. The guy wire and the ground would be this angle here. So that's what we are looking for. So in this situation, we don't know the opposite in this situation. What we do know is we know the adjacent and we know the hypotenuse. So when we know the adjacent and the hypotenuse, we're going to use cosine to help us calculate that. So cosine of our angle theta would be equal to our adjacent, which is 9.6, over our hypotenuse, which is 15. Obviously, we're looking for the angle, so we're going to use cosine inverse of 9.6 over 15, and that will be equal to theta. Calculating that out, second cosine inverse of 9.6 divided by 15, we end up getting that that angle is 50.21 degrees. Right? That is the angle. We call that an angle of elevation. If we were standing up on the ground, that we would have to look up to see it. Now, there is a second part to this problem, and this is what it says. It says calculate how far up the tower the guy wire is going to attach. So if we want to know where it's going to attach, essentially we're looking for x. Now, in this situation, we can do this one of two different ways. We can either do it using the hypotenuse, or we can do it using the adjacent. 15 is a nicer number, so let's just use that one. So if I wanted to use the hypotenuse, this is my opposite side. I'm going to use sine. So I'm going to say sine of my angle, which we just found was 50.21, is going to be equal to my opposite, which is x, over my hypotenuse, which is 15. So to solve this, I would multiply both sides by 15 to isolate x. So I have 15 times the sine of 50.21 as what x is. So coming over to our calculator, 15 times the sine of 50.21 will give us a height of 11.53 is what x is equal to. Right? So in this situation, our wire is actually longer than what our tower actually is. And that's fine. There's nothing that says otherwise. I mean, really, that should actually make sense because this is operating along the hypotenuse of the triangle, so the wire should be longer than everything else. Let's take a look at another one. It says an airplane is flying at 13,000 feet above the ground. The angle of depression from the plane to the base of a tree is 21 degrees. So we have our little airplane. Here it is. The wing, the other wing, the tail, the cockpit. This guy's flying. Now his normal line of sight is going straight out, and that is parallel to the ground over here. Now somewhere down on the ground we have this lovely little tree. For all intents and purposes, this is definitely not to scale. Now, what it does tell us is that the angle of depression from the plane to the base of the tree is 21 degrees. So what that means is that if my pilot up in the cockpit decided to look down and he saw this tree, right to the base of the tree, let's just get it to the base of the tree. I can do a better drawing than that. So here it comes. So if he decides to look down to the exact base of the tree, he needed to look down 21 degrees. Now, it says how far horizontally must the plane travel to fly directly over the tree? Well, a couple different things. We know first off that if we fell straight down, we would have to fall down 13,000 feet because that's how high above the ground we are flying. So the right triangle we're going to use is actually right here. Now, one thing about this is that since his line of sight is parallel with the ground initially before he looks down, we know that this is going to form a right angle up top. We already know that part of that right angle is 21 degrees, so whatever's left must be the other part in the top of that triangle. So 90 minus 21 means that we are left with a 69 degree angle right here. Now, essentially what we're being asked to find is we want to know how far does that airplane need to travel before it's over the tree, which is x in this situation. So we have our 69 degree angle up top, right? We've set our problem up with that, so let's use that angle. Since this is our opposite side and this is our adjacent side, we want to use tangent to do it. So the tangent of 69 degrees is going to be equal to x over 13,000. Now to get x alone, we're going to have to multiply both sides by 13,000. So I'm going to have 13,000 times the tangent of 69 is equal to x. So multiplying that all out, 13,000 times the tangent of 69 degrees gives us an answer of x being equal to 33,866 0.16, I think we're talking about feet in this problem, feet. So really, that airplane still needs to travel multiple miles in order to actually get over that tree because of how tall or high up in the air he is. Looks like we have one last problem, so here it is. It says a 200-foot tower casts a 40-foot shadow. So here is our tower. This is 200 feet tall. It is casting a shadow that is 40 feet. So here is the shadow. And that shadow is 40 feet. If a person is standing at the end of the shadow, so a person is standing right over here, and they look up to the top of the tower, what is the angle of elevation from that person's eyes to the top of the building? Now, what they want us to assume is that the person's eyes are 5 feet off the ground. So when we think about angles of elevation and angles of depression, remember, their normal eyesight would go out straight. So if his eyes are 5 feet off the ground, then he's going to be looking at a spot that's 5 feet off the ground of that building. Now, we said that this person decided to move their gaze and look to the top of this tower. So they shifted their gaze upwards, which is our angle of elevation. Now, in this particular situation, they want us to find the angle of elevation. So this is the angle we're looking for. Now, a couple of things. We do know that this distance represented here is still going to be 40 feet as it was for the shadow below it. And the building's going to change just slightly. So we're thinking about it in terms of this triangle now. So the whole building was 200 feet tall, but when we started thinking about this, we're coming from a stance of this 5 foot is going to be kind of wasted in terms of this triangle. So this side of the triangle will only be 195 feet tall. So coming over here, if we want to find this angle, we know the opposite side and the adjacent side. So we're going to use tangent. So we're going to say tangent of our angle is equal to our opposite, which is 195, over our adjacent, which is 40. To solve this, we are looking for the angle, so we're going to use tangent inverse, which means we flip where the fraction and theta sit. And when we punch that in on our calculator, we are going to get second tangent inverse of 195 divided by 40. And that's going to give us an answer of 78.41. So theta is equal to 78.41 degrees. So if I'm standing here and I wanted to look up, I have to tilt my head up 78.41 degrees to get up there. Thank you guys so much for watching the full video. If you have any questions, please make sure you are reaching out and asking. I hope you all are well. Thanks, guys.